Hi class, we're now going to discuss 8.7, which is enthalpy. Enthalpy has to do with heat. If any of this may seem a little foreign to you, I put on here to review the parentheses moved. 3.12, that's when we were dealing with specific heat, so calorimetry. This may sound, that may allow some of this information to come back to you. So enthalpy, chemical reactions can be exothermic, which means that they emit thermal energy, also known as heat, when they occur. So if you stand by a fire, that's an exothermic, you can feel the heat. Or chemical reactions can be endothermic, which they absorb thermal energy. A perfect example is an ice cube that is pulling energy from your hand into the ice. So that's an endothermic and leaves your hand cold because the energy is being pulled away from the heat's being pulled away from your hand. The amount of thermal energy or heat emitted or absorbed by a chemical reaction under conditions of constant pressure is called enthalpy. So it's a fancy term for the measurement of heat. Under the condition has to be under constant pressure, which means open to the atmosphere. So if you do experiments to determine the heat of something, it's just at constant pressure means open to the atmosphere, not an isolated like a thermos or something that is away from the open atmosphere. Okay, so enthalpy is a H, and we put a delta, so it's a change in heat, change in a reaction. So we define this as enthalpy of reaction, delta H, as the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. Again, review 3.2. At constant pressure, that also means Q. This is where I want you to review 3.2. Q is the heat. So if you remember specific heat values, we would use Q to determine the value that had been exchanged from one system to a surrounding and so forth. So at constant pressure, H equals Q. And what delta H means is that the difference from the products, reactants from the products, if Q, the value of Q is less than delta H, so it's negative, then it's an exothermic reaction. And if it's endothermic, it's a positive reaction, which means that you have a positive value. So we're going to start actually looking at values here. But let's understand H. So the sign of enthalpy, the change in enthalpy, depends on the direction. So the sign is basically indicating which flow the energy flows. So if energy flows out of a system, then it's like a withdrawal. So this is like pulling money out of a bank. It's negative. You're pulling money away from the bank, the ATM. Energy flowing into a system is like a deposit and carries a positive sign. So that's depositing money at the ATM means it's going to be positive. Okay, but if we look at reactions, an exothermic reaction, energy is released into surroundings. And what that is here is an arrow with energy. This means that the reactants have more energy than the products. And when the products are formed, energy is released in the form of heat, which is what we feel. If it's an endothermic reaction, so here's the energy as it increases, the reactants are lower in energy than the products, and they will pull energy, excuse me, they are absorbing energy in order to produce the products, which are at a higher energy level. So let me repeat that. I think I'm not saying it right. The reactants are at a lower energy. The products are a higher energy. So energy needs to be absorbed in order to have the products proceed to be produced. So this energy is needed in order to get to the products, which is at a higher level. When thermal energy flows out of a reaction into the surroundings, again, that's negative. We're going to take a look at a reaction that is negative. So this is methane, and methane is a natural gas in the presence of oxygen. This is a combustion reaction, and combustion reactions produce CO2 and water. So methane being produced, you would feel heat. This is a negative enthalpy, change in enthalpy. This is a negative 802.3 kilojoules. So that's the amount of the measure. Remember I told you it's a measurement of heat. The amount that's given off by this reaction, and it's negative. This reaction is exothermic. The magnitude tells us that that's the actual value. Tells us 802.3 kilojoules of heat are emitted with this exact reaction, meaning it takes 1 mole of methane and 2 moles of oxygen to produce this value that's given on the right. But let's look at another one. So when thermal energy flows into the reaction and out of the surroundings, goes from the heat being pulled from your hand, as an example. Here we have nitrogen and oxygen, which produce NO. This is an endothermic reaction, and it's positive enthalpy. The magnitude, tells us that we have 182.6 kilojoules of heat absorbed. So this is being absorbed from the surroundings with this exact ratio of compounds. So with 1 mole of nitrogen and 1 mole of oxygen, it produces positive 182.6 kilojoules. So the amount of heat emitted or absorbed when a chemical reaction occurs depends on the amounts of the reactants that actually react. So that's why I'm specifically saying these amounts give this value. If we change these amounts, these coefficients, then the value will also change. We usually specify delta H in combination with the balanced equation for the reaction. I don't know what happened here. I don't know what that is. The magnitude for the stoichiometric amounts of the reactants and products for the reaction as written. I don't know what happened. The magnitude is basically telling you if it's a positive or negative. You're writing the positive or negative to let the person that's reading this understand the direction of the energy flow. Okay, so here's for balanced equation. Again, we're using propane, and we can see that with this exact ratio of coefficients, it produces a negative 2,044 kilojoules. If we change any of these, that's not going to happen. But we can also use it as a conversion. So 1 mole of propane reacts with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water. So with this amount, there's a ratio of anything with this. So let's take a look. All right, so to find out how much heat is emitted upon a combustion of a certain mass in grams of propane. So basically what we're saying is that we want to determine, if we're given a specific mass, how much heat or how much anything that we can use from this. So in this case, if we're given a certain mass, we want to know how much kilojoules of heat is being produced. Now I want to go back and go with this ratio thing. This amount is equivalent to any of these for conversion. That means 1 mole of propane equals this amount, 5 moles of oxygen equals this amount, 3 moles of CO2 equals this amount, 4 moles of water equals this amount. And we can set it up as a conversion like you see it here. So if we needed oxygen, we could put oxygen, and we would have to have the correct moles for that, and so forth. So this reaction with this value we can use as a conversion or a ratio to each other. So in this case, if we're given a certain mass, we can get to the moles, and that'll give us to the kilojoules. And the moles is going to be for whatever substance we need here as moles, plus this value, because the kilojoules is what we're going to need at the end. And you have to bring the sign with it. So calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So we're given an amount of 11.8 times 10 to the third grams of propane. So we're going to set this up. Grams, the amount that we're given would be here. We need the molar mass, so that's not changing. And when it comes to stoichiometry, we're still doing the molar mass. The only thing that's different is that we're using a different conversion, which we can use, which is the amount of enthalpy that's been produced from a specific reaction. Then we have our moles of propane. We pull from the equation the amount that can be produced from that specific balanced reaction, and that mole amount from that reaction, which is 1 mole, is equivalent to negative 2,044 kilojoules of heat. And now we can cancel out the moles, and it'll give us the kilojoules. And you can see these are the relationships that we used. Okay, so we set this up. We're given the amount of heat we want to determine how much heat can be, we're given the amount of gas that we need to determine how much heat can be produced from this. So in this case, we have our molar mass, and then we use the conversion of our enthalpy, measure a change in enthalpy versus whatever substance in that balanced reaction, which is in this case is 1 mole of propane. And this produces negative 504.47 times 10 to the 5th kilojoules. Often in homework, the absolute value of Q is requested as words. So basically, remember the Q. I'm going back to Q here. Let's go back. It might, if it's specifically asking for something without the sign, it's asking for the absolute, then that means that you don't add in the negative sign. However, in this case, it didn't specifically ask for it, so the negative sign came with this, and we leave it, our answer, in the negative. So enthalpy of reaction, the amount of heat released or absorbed by a chemical reaction under conditions of constant pressure. So the magnitude of the change in enthalpy is associated with the stoichiometric